This is example number 2 on failure theories for ductile materials. In this particular example, consider this bracket and has a load F applied at this end. And what you're asked for is, what is the force F? What is the value of F to maintain a safety factor 1.5 or a design factor in this problem of 1.5. So this is given in the problem. And the location that you are interested in finding all this is this location A. We could have chosen O, but let's just choose the point A and evaluate what's happening here. Okay, we know that your problem will be safe whenever your safety factor, your factor of safety is actually bigger than 1. Bigger or equal than 1. 1 is onset of failure. Bigger than 1 is completely safe without any problem. So the problem does give me some information here. It does give me my tensile EO strength of 81 KSI. It gives me my elastic modulus E equal to 30,000 KSI. And this is a ductile material. Steels are considered ductile. So therefore I can say basically this is approximately the yield strength is the same in tensile as in compressive for given the lack of information that we have. Okay, so let's start the problem. And if at this location you resolve the loads from here to here to here, and you do all that exercise, you can show that if I had the cross section here at the location A, cross section at A, you're going to have the following. You will have your Vy is equal to minus F, Mxx is equal to 15F, Myy is equal to minus 14F. Okay, so at this particular location, assuming I'm taking the location at the top, you can, I'm sorry, this is MZZ. What you can show in the problem is that if this is Y, this is X, and this is Z. So what you can show is that your load, this load is negative, right? So that means it's rotating about this axis in this direction, right? Creating a moment in this direction. So therefore, this side will be in tension, and then this torque is positive going in this direction, generating a torque like this about this axis. So that means this torque will be tau xy xz. This will be sigma xx. And I don't really care for this load. We will not play a big role, will not play any role at point A. Okay. So I have a factor, a design factor 1.5 that I need to apply. So if I apply the design factor, the loads that I will use in my problem are the following. I'm going to use 1.5 minus F is going to give you 1 minus 1.5 F. Mxx will be 1.5 times 15F, and that will give you 22.5 F. Mzz will give you 1.5 times minus 14F, and that will give you minus 21F. Okay, so we know that your state of stress at location A is going to look as follows, right? Sigma xx and 0, I don't have nothing across here. I only have a torsion value. everything else is exactly equal to 0. And we know that sigma xx is equal to axial load plus sigma xx in bending, but we do not have any axial loads in our problem, so it is only equal to bending. And we know that your bending, your xx in bending will actually equal to mzz divided by z. And in your torsional value will be mxx divided by q. Okay, so this is the information that we get from the problem. Now, the values for z and q come from the tables. And from the tables, we find this is equal to pi d cubed over 32. And q is equal to pi d cubed over 16. So what you have to keep in your mind, the small d that we want to use in the problem, this small d is this diameter, okay? The diameter of the smaller section, not the biggest section, okay? So this would be the location, the small d that we are using. So in our problem, in general, you have this is equal to mzz over z, and then we have the torque z is equal to mxx over q, where this small q is d. And what you have to know in our problem is every time we have a discontinuity like that, we have to have a stress concentration value. Okay. However, the problem says this is the problem says we are working with a steel bracket. Okay, it's steel. So therefore, since this is steel, the problem is ductile. Since the material is ductile material, then the stress concentration values are actually equal to 1. Okay, so basically I don't have any in this particular problem. Okay, so if I replace all these numbers in here, replace all the values, you can show that your new state of stress is actually equal to following. It's equal to 213.9 F, 0, 114.6 F, 0, 0, 0, and this is a symmetric matrix, a tensor, F, 0, 0, okay? Now, what I need to do in my problem, what I'm interested in, and what we want to do is from here, since you work in ductile materials, I need a couple of information. I need sigma 1, I need sigma 2, I need sigma 3, and I need tau max. Now, you might say, how do I do this? Well, I can actually, we can use our code without any problem at all, because in our code, we can write it like this, 213.9 F. Let me forget about the F for a moment. 114.6, 114.6. And note, I can multiply the whole thing by F. I can take it outside because this factors out, right? The multiplication of a matrix times a scalar is each one of the components multiplied by F. So I could do that. So therefore, I can use the Matlab code that we have as it is and find the values and add the letter F at the end. Now, the theories that we want to use, we got 3 theories, right? The first theory is the distortion energy theory that says sigma equivalent is equal to tensile yield strength, sigma equivalent. The second theory is maximum shear stress theory that says that sorry, this is factor safety here. So here I need to find this. In this theory, it says that uh, your yield shear strength is over tau max. In this particular theory, we take this as half of my tensile yield strength. And what I need is this. And then another theory that actually gives you the same value when we work in the case of pure shear is the distortion energy shear stress theory. And that theory says factor of safety is also the expression is almost identical. The only difference is that here we are going to be using sigma yield over square root of 3 or 0.577 sigma yield tensile. This is going to come very handy, especially when we work with springs and fasteners. We're going to use this expression a lot more than we're going to use this. So it's important to get used to and familiar with it. The last theory that we have is the ductile column Moore theory. And that theory basically says your factor of safety is going to equal to 1 over sigma 1 yield in tensile minus sigma 3 yield in compression. Okay, and since these are basically the same, so then these two basically give you the same answer. Okay, so now the question is, how do we go about this, knowing that these are the theories I want to work with? Before I do anything, I need this information. So let's go ahead and see what your Matlab code gives you. And we can run the Matlab code as follows. Okay, again, use the location that says here main failure theory. Okay, that's the main problem you're solving, and you run it. When you run that code, I'm down here now. Everything is in inches. It's in PSI. And do I have a design factor? Well, remember, I already multiplied my design factor, right? But let's suppose I didn't want to multiply it and I want to let the code do all the multiplication. Then let's suppose I'm taking this equal to, I'm going to add it here, 1.5, to see if I did my multiplication correct. And when I'm working in this case, it's the case of loads. That's what I know. And it's a circular section, so I pressed number 3. And the diameter was 1 inches. And the axial load, I didn't have any axial load. I did have a torsion load. And the torsion load was 15. Remember, I'm forgetting the F. Ignore your letter F. Okay? And your bending is equal to minus 14. Your shear is equal to minus 1. And this is ductile material. And the yield strength for this material, we found that was actually equal to 81. We're going to assume that since it's ductile material, they're basically the same value. This is 30,000 is given in the problem. Running the code again. And then you run the code. Your code runs. Okay. So this is what you will get. You're going to get these values right here at point A. Okay. And I give you the point A and point B because we always want to compare. Many times, even if you're adding stresses, sometimes when both are in, the tension is higher than compression, then actually you can have a different values. In this problem, it's not going to be an issue, but you do have both of them. And it tells you the design point could be either A or B for this particular problem. How do I interpret these results? So let's go back here. We can scroll all the way up here, and you can see that your problem that's here, this is given in completely in KSI. So what's happening here, this is actually 213. If you look at it here, this is the value 213. Don't worry about the minus sign. Oh yes, this is point C. That's where there's a minus sign. So we can go all the way up. This is positive. So this is actually given in KSI is divided by 1,000. Okay. So it's 213. This is 114. This is 114. And you can see you get exactly the same value. Okay. So your stresses that you are getting, okay, your principal stresses are these stresses right here. And these stresses are, then you can check these stresses. Let me check the stresses from my code and bring them right there. And let me show you, but this is not KSI. This is in KSI. If you wanted to write all your values in PSI, then your value would be sigma 1 is equal to 260 F. This will be in PSI. Sigma 2 will be 0. Sigma 3 will be minus 50 F. And everything is in PSI here. So these are the values I use for our analysis purposes. Okay, so using this, and also from the code, you can also get what the value of tau 1, 2, 3 is. You see, the tau maximum. So the value of your tau maximum in the problem, and then this comes from your old stuff that you should already know. This is KSI. I need to add the letter F because remember I extracted that. And that will give you 160 F KSI. Okay, so these are all the loads that I actually need for my analysis. So now we move on to complete the analysis. Okay, so then now that we have our principal stresses and all the information that we need, we can go to distortional energy theory. And the distortion energy theory says this is equal to sigma 1 squared plus sigma 2 squared plus sigma 3 squared minus sigma 1 times sigma 2 minus sigma 2 sigma 3 minus sigma 1 sigma 3. And you replace all the values here. You can show that the value that you get is actually equal to 292 KSI. And remember, I factor out the F so I can put my F back. And if you want to look how the Matlab code works, you can go to the Matlab file. And you see that the Matlab file actually gives you that value. It replaces all the values and gives you this. This is the value you will be using. So with that said, now you can basically say your factor of safety is equal to your yield strength divided by sigma equivalent, which is actually equal to 81 divided by 0.292. And that has to be bigger or equal than 1. And this is F. Okay? So now when we solve for this, you can see that the value that you're going to get here, this value that you're getting here, this value, it is the value that you get from your code. The code you get 277 is that value right there. That is that ratio. So basically what you're saying is this is 277 divided by f, so bigger or equal than 1, because my f was at the bottom and this ratio was equal to this. So basically for this theory, we are saying that f has to be less or equal than 277. Okay, your next theory is the maximal shear stress theory. In the shear stress theory, we need tau max. Tau max we already found is 160, or it is 0.160 KSI, and I need to add the letter F. So it says your factor of safety will be yield strength in shear tau maximum, and that will be it gives you a value of the exact number here, by the way. This is there was round off. The exact number is 0.157, and if I am doing this, this is 80 divided by 2, so this would be 40.5 divided by 0.175 divided by f, and that has to be bigger or equal than 1. Note that I am using here 0.5 times sigma yield in tensile. Okay, this value that I get here is the value that we'll get from the code for your factor of safety. So if you look at the code itself, the value that I'm getting here is 258. So you can write here, this is 258 divided by f, bigger or equal than 1, or say f has to be less or equal than 258. Then your next theory that's very similar to this theory uses the distortion energy shear stress theory. Basically, what it says is you're still going to use your tau max that was equal to 0.157 f. Remember, the f is important. So this is all in KSI. And your expression looks almost or identically the same. The only difference is that here the value that we are using is for my shear yield strength is 0.577 sigma yield tensile. And that gives you a value of 46.76 divided by 0.157 f. This has to be bigger or equal than 1. So again, the value that I get from the code will be the ratio for this. And you can see what I'm getting from the code. You get the code, the value of 299, 298. Okay, so this is the value that you place here. This is 298 divided by f has to be bigger or equal than 1, or f has to be less or equal than 298. The last theory is the Brittle-Collomore, and the Brittle-Collomore theory says for ductile, I'm sorry, not brittle, Ductile-Collomore theory says that your factor of safety would actually equal to 1 over the absolute value of sigma 1 divided by sigma yield in tensile minus sigma 3 in sigma yield in compression. Okay, so if I replace the values in there, or replace all the values, you will find that this actually gives you 1 over, this is sigma 1 is 0.64 f divided by 81 minus 0.05 f divided by 81. This has to be factor safety, and this has to be bigger or equal than 1. Okay, so if I do the math here now and I solve for my f, so I can solve for f, and you can show that your f has to be bigger or equal, less or equal than 258. Now you can do this also using your Matlab code, and that's the value that you get over here. Okay, so when you do all this, at the end of the day, at the bottom of the code, when you scroll all the way down here at the bottom of your code, at the end of the code, you find these values, and these values are basically a summary of all the values of f that you're going to get for various cases. So I am, just give me a second. Okay, so these are the values that you get. You're getting for all the 3 cases. And I want to do a small table here just to show you the values that we get. Okay, so these are the f, the value of f. This is distortion energy, and says the maximum value of f is 277. Here, maximum shear stress theory says maximum value is 258. The distortion energy shear stress theory says that this is 298, and your ductile column Moore theory says this is 258. And you can immediately see which one is the most conservative one. This is the most conservative one. Why? Because this is asking for a smallest possible value of my load. This one is the one that we typically use in the industry because it's been shown that all the test data actually applies to the distortion energy theory. So it's not, there's no value of adding extra burden to your analysis of forcing your load to be this small when you can actually buy some more load. Okay, so this results show again, this is very conservative. Okay, and these two will produce the same results if your sigma yield has exactly the same value. Okay, so now let's go to the next problem. Next problem is a small, it's a flip to this problem. And in this particular problem, let's use, so in this particular problem, let's use the same design factor of 1.5. And the problem is basically saying the following. The following is saying, I am giving a load of 400 pounds and a load of 270 pounds. Will the component fail for each one of these cases? So the best way we can do this problem is, let's go ahead and let's do a table. We already did this table in this chart in the previous slide, but I would like to repeat the table again. 2 rows, and this is going to be the value of f. This is what we want to check if it's going to be safe or not. This is distortional energy theory. This is maximum shear stress theory. This is distortion energy shear stress theory. This is ductile column Moore theory. And what you see here in these values is we got the value of 277. We got here 278. We got here 298. We got here 258. Okay, those are the values that we got. Now, let me take this away from here for a moment, and what I'm going to do is I am going to copy separate tables here, okay? And we will do this separately. The other one was, the other case was 270, okay? So now let's see what happens. So this is 270 and 200 and so for 240, for 400 pounds, this exceeds this value, so it fails. This fails. It fails. It fails for all the possible theories. So it failed for all four theories, and it fails because the load exceeds, even exceeds the maximum load that you could possibly have. So you know that this is just not a valid option. When you go on this side and now on the other hand, this one you can say, hey, this is safe. This one actually exceeds this value, so it fails. This one is safe as well. And this one fails as well. And this is the one that we typically care for and we look for, and we say safe. So if it's safe, we can say the load is acceptable. Load is acceptable for distortional energy theory. Okay, so that would be the answer and conclusion of this example number 2.